Third part of gaseous state, viscosity. It is well known that all liquids do not flow with the same speed. Some liquid like water, ether, etc. flow rapidly while some other liquid like glycerin, castor oil, etc. flow quite slowly. This indicates that every liquid has some internal resistance to flow. The internal resistance to flow possessed by a liquid is called its viscosity. The liquid which flows slowly obviously have high internal resistance and therefore are said to be more viscous or are said to have high viscosity. On the other hand, the liquid which flow rapidly have low internal resistance and hence are said to be less viscous or are said to have low viscosity. To understand the nature of the internal resistance or frictional existing within a liquid, consider a liquid flowing through a narrow tube. All part of the liquid do not move through the tube with the same viscosity. Imagine the liquid to be made up of a large number of thin cylindrical coaxial layer. The layer which is in contact with the wall of the tube is almost stationary. As we move from the wall towards the center of tube, the viscosity of the cylindrical layer keeps on increasing till its maximum at the center. Conversely, we may say that as we move from the centers towards the walls, the velocity of the layer keeps on decreasing. In other words, every layer offers some resistance on friction to the layer immediately below it. This force of frictions which one of layer of the liquid offer to the another layer of the liquid moving with a different viscosity is called viscosity. It has been found that the force of frictions between two cylindrical layers which each having area a square centimeter separated by distance x centimeter and having a velocity difference of v centimeter per second is given by f in directly proportional a into v by x or f equal to n a v upon x where n is a constant known as coefficient of viscosity. If x is equal 1 centimeter, a is equal 1 square centimeter and v is equal 1 centimeter per second, then f equal to n. Hence coefficient of viscosity may be defined as the force of frictions derived to maintain a viscosity difference of 1 centimeter upon 1 centimeter per second between two parallel layers 1 centimeter apart and each having an area of 1 square centimeter. For example difference, we write f equal to n a dv upon dx as dv by dx is called velocity gradient. Some important result related with the property of viscosity are follows. Fluid the reciprocal of the coefficient of viscosity is called fluidity. It is usually represented by a phi. Fluidity is in fact measurement of the case with which liquid can flow through a capillary. It was shown by Usually that the flow of a liquid through a capillary tube is governed by the following expression: n equal to pi p r की power 4 t by t 8 vl, where v is the volume of the liquid that flow in time t under a constant pressure p through a capillary tube of L and radius r. N is the coefficient of viscosity. 3 unit of viscosity and fluidity as already described. F equal to n av upon x, n equal to f multiply x upon a multiply v, times multiply centimeter upon centimeter cube centimeter square multiply centimeter second minus power equal to 9 centimeter minus 2 centimeter. Thus the units of viscosity are 9 second centimeter power minus 2. This quantity is called poise. Poise going to high a big quantity. Therefore, sometimes smaller units are employed such as centipoise or millipoise. This unit of fluidity are poise minus 1. For effect of temperature on viscosity, with increase of temperature, the kinetic energy of the molecule of the liquid increase. Hence, the liquid start following faster. In other words, the viscosity of a liquid decreases with increase in temperature. It has been found that the decrease is about 2% per degree rise of temperature. A number of equations can be proposed connecting viscosity and temperature. The best out of these is the given by Arians for pure liquid. This equation is n equal to a e power e by rt, where a and e are the constant for the liquid and t is the absolute temperature. E is called activation energy for viscous flow. The above equation may be written as log n equal to log a plus e by rt. Thus the plot of log n versus 1 by t is straight line with slope e by r. Measurement of viscosity. The absolute value of the coefficient of viscosity can be determined by measuring the various parameters involved in the Poiseuille's formula. N equal to pi p r की power 4 t upon 8 VL. However, for the most of the purpose, it is sufficient to find out the relative viscosity. Viscosity with respect to water as reference. This eliminates the necessity of the measurement of a number of parameters of the above formula as explained below. For a liquid flowing under its own hydrostatic pressure P equal to HdG, where H is the height of column, D is the density, G is the acceleration due to gravity. Here formula is N equal to pi into HdG into R power 4T upon 8VL for equal volume of two liquids flowing from the same height h through the same capillary, that the length L and the radius are the same. If N1 and N2 are the coefficient of viscosity of the two liquid D and D2, their density and T1 and T2 they are the respective time of the flow. N1 upon N2 is equal to pi into HD1G dot R power 4 T1 upon 8VL multiply 8VL upon pi HD2G dot R power 4 T2 equal to D1 T1 upon D2 up D2. Thus, measuring the time of the flow of two liquids, knowing their density and knowing the coefficient of viscosity of one of the liquid, that of the other can be calculated. The apparatus used for the measurement of relativity viscosity based upon the formula is called a viscometer. The simplest is the one given by Oswald and is called the Oswald's viscometer. It is shown diagrammatically in figure. It consists essentially of a bulb B to which is sealed a tube above and a capillary below. There is a mark M on the tube and mark M dot on the capillary, as on the lower end of the capillary is a shield to a bigger bulb C and a wider tube DE. The complete apparatus is U-shaped. The procedure consists of the following step. One apparatus is first washed with chromium acid and then thoroughly with water. It is then clamped vertically and a rubber tube is attached to the end A. A definite volume of water is introduced into the bulb C through the end E. The quantity of water added should be more than that required to fill the bulb B through the rubber tube attached to the end A. Distilled water is shooked up into the bulb P so that the level of water is a little above the mark M. The water is then allowed to flow back and time taken for the water to flow from the mark M or M to M dot is noted. The apparatus is taking dried and the experimental is repeated as above, taking the same volume of experimental liquid. The result is then calculated using the formula derived above. The value of the coefficient of viscosity at 20 degrees Celsius for some common liquid are recorded. Liquid crystals. A large number of organic compounds with long chain molecules, cholesterol acetate and cholesterol benzoate, para-hexoxyanisole CH3O benzene NO double bond and benzene OCH3, ammonium oleate C17S33 COOO NH4 etc. are known, which on heating melt sharply to give a milky liquid which on further heating become clear again at a definite temperature. The former temperature is called the transition point, where the later is called the melting point. On cooling the clear liquid, the reverse change take place exactly at the same temperature. The turbid liquid thus obtained are found to be anisotropic. Anisotropic, a property is possessed by crystalline substance according to which the property like reflective index, electrical conductivity, etc. are found to be different in different directions. Hence, these true bit liquids are called liquid crystal. However, it is the found that the molecule of a liquid crystal do not have the arrangement like that of a crystal lattice. However, except of a for a few properties, they behave like true solid. They possess surface tension and have the property of flow. Hence, in space of liquid crystal, certain other name we have proposed such as anisotropic liquids or paracrystal. The best name for the substance in state is mesomorphic state. However, in spite of all this, the original name liquid crystal is still frequently used. Type of liquid crystal. On the basis of their molecular arrangement, the liquid crystals are classified into the following three types. First, nematic liquids. In these crystals, the molecules are lined up in such a way that their long axes are parallel to each other, but the molecules are not arranged in layer. The parallel molecule can slide past each other. The name nematic becomes comes from the Greek word meaning thread, as they appeared thread-like when seen under a microscope. The crystals are translucent, less turbid, and quite mobile. Can flow further. They scattered light strongly. Second, schematic liquid. In these crystal, in the molecule do not only have their long axes parallel to each other, but are also arranged in layers. These parallel molecules in planes can slip past each other. The name schematic has been derived from the Greek word meaning soap, as these crystals are like soap in touch and structures. These crystalline are more turbid and viscous than pneumatic liquid crystals. Frequently, a schematic substance is transformed into a pneumatic substance during the course of heating to a higher temperature. Some example of the compound yielding schematic type of liquid crystal. Third, cloistric liquid crystal. In this crystal, the arrangement of molecule is similar to the of molecule nematic liquid crystal. However, in this crystal, the orientation of the axis shift in a regular way in going from one layer to the next, thereby giving a helical structure. Because of this structure, cholesteric crystals have the remarkable optical property of reflecting light of different colors under different conditions at different temperature. Based upon this property, ring using cholesteric liquids crystals are available which change a color with person's mood. With one skin temperature, the name cholesteric has been given to these crystals because these substances are all derivative of cholesterol. Use of liquid crystal. First, liquid crystals are used in wrist watches and other electronic instruments in which a digital display of black number take place against a silver background. Second, thin films of cholesteric liquid crystal are used to map skin temperature as and aid to the diagnosis of disease tissue and in the ring to study person's mood as already explained. Difference between liquid crystal solid and liquid. The main difference between a solid, a liquid and a liquid crystal is the long range order and their molecule. In a crystalline solid there is a complete long range order there, whereas in a liquid there is almost complete long range disorder or there is almost no wrong order at all. Liquid crystal respect a mesomeric state, an intermediate state between a solid and a liquid. They do not have a perfectly ordered arrangement of their molecules like that of a solid, still have more ordered as observed from X-ray uh, diffraction study. Further, as already mentioned, some crystalline solid on heating from schematic liquid crystal, whereas some other give pneumatic liquid crystal. Both these type of liquid crystal have less order than a solid but greater order than a liquid and Also, symmetric liquid crystal have been older than nematic liquid crystal. There are some crystalline solid which no on heating first form symmetric type of liquid crystalline which on further heating from pneumatic type of liquid crystalline which on known further heating melt to form the clear liquid. A common example of this type is that of cholesterol myristate. The change may be represented as follow: cholesterol myristate into symmetric liquid crystalline into pneumatic liquid crystalline into liquid. Thus, there are two transition temperature and one melting point. To represent the structural difference between a solid symmetric liquid crystal, nematic liquid crystal, and a clear liquid, diagrammatically, let us take the example of a crystalline solid of the type of cholesterol maestrate. In the crystalline solid, there is a complete long range order in the three-dimensional. All the molecules have the same orientation and have a regular arrangement in different planes are shown. Overheating it form a turbid liquid called a symmetric liquid crystal. In this state, all the molecules have the same orientation and they are in equispaced planes, but the arrangement within the plane is irregular. The substance is no longer a true crystal, although it has more order than a liquid. On further heating, the turbidity decrease and a particular temperature in state is obtained called nematic state, in which molecules still have the same orientation but they are no longer in equispaced planes. Thus, more disorder is introduced, yet some order is mentioned because all the molecules still have the same orientation on further heating. Even this order is lost and the substance is in the liquid state. Thermography. It is a technique of the recording the temperature variation exactly of the skin or a graph. And the graph and the record thus obtained is called a thermograph. It is based upon the fact that because of the helical structure of the cholesteric liquid crystal, they have the remarkable optical property of reflecting height of different color under different temperature. This is because the helical structure has a characteristic pitch length. These pitch length are in the range of wavelength of the visible light. The pitch length change on the changing the temperature, but the chemical structure of the helix remains ineffective. The property of different liquid crystal are described in terms of uh, event temperature and the clearing point temperature. The lowest temperature where liquid crystal scattered visible light is called the event temperature. At a temperature below this temperature, the liquid crystal will be in the solid and will appear transparent. The temperature above which is become pure liquid is called the clearing point temperature. Depending upon the requirement, the suitable liquid crystal can be selected which reflect light of different color in the desired temperature range. The most important application of thermography has been in the medical field in the recent years, exceptly in the clear earlier detection or diagnosis of tumor of breast cancer. Beside orthopedic disorders such as arthritis and back pain, etc., the basic principle is that the heat change produced in the affected skin are different from the highly skilled. Earlier, the Saigicans used to paint the liquid crystal on the portion of the liquid to expand, but this method was too rough. Now the method is simple. The liquid crystal are pressed against the healthier part as well as the part to be explained, and the color photograph are taken of the resulting pattern of the colors and then compared. In fact, the principle of thermography has been in use since very early times. Ancient Greek physicians employed a primitive method of thermology. They used to apply a thin mud slurry on the area of their patient's body and observe the pattern of drying and therefore determine the abnormal distribution of body heat. This technique was called medical thermography. Liquid crystal display and seven segment cells. One of the most important application of liquid crystal has been in the electronic industry. They are being used in thin, light weight display device such as digital watches, pocket calculator, and similar instrument. As this is done with the help of liquid crystal, it is called the liquid crystal display. The basic principle is as follows: a thin film of a film liquid crystal not more than 1 thousand of an inch thick is placed between two sheets of glass, one of which is coated on one side with a thin layer of an electrical conductive material such as tin oxides. When no current is passing through the conductive coating, the molecule are uniform oriented and the light can pass through the cell. When the current is applied, the molecular alignment changes and the cell appears opaque or black. Thus, a number or a letter is displayed in black against a silver background. As a liquid crystal display requires a very small current. It consumes very little power. Electronic watches and calculators run for years with a small battery. Most of the displays in LCD watches and calculators are composed of several seven segment sections. Each seven sections can display one number. The combination of these sections displays the number. Similarly, for alphanumerical display, there are 14 segments. The complete display panel is composed of two polarizers that transmit light in perpendicular direction, a mirror surface, and a layer of liquid crystal material between two glass plates as shown in figure. In absence of the applied voltage, the liquid crystal molecule in all segments are precisely alignment. Therefore, the entire panel appears silvery because light passes through both the polarized and reflected back by the mirrored surface and then again passes through both the polarized. When voltage is applied to the segment of a display, the precise alignment of liquid crystal's molecule is lost. This results in the polarized light from the first polarizer not being rotated by the required 90-degree to align with the second polarizer. The second polarizer blocks the passage of the light and cause that segment of the panel to appear complete the gaseous state.